So we've been looking at how to present and describe patterns in our data. And so I'd like to briefly highlight three statistical measures that are commonly used in describing patterns so that you kind of have the ability to recognize what they are, when they would be used, what they're communicating, and how to interpret them correctly. And so I'll begin with what we would use if we have categorical data. So if we have data that could be organized into a table, we can conduct a statistical analysis of that table to figure out, is there a pattern here? And there's dozens actually of statistical tests that you can use. However, the two that I think are probably the most versatile and probably the most widely used would be gamma and the chi-square test. And so I'll just kind of talk through sort of how these things differ. Gamma only works if you have ordinal variables, because gamma is looking for a relationship, not just does a pattern exist, but is it a positive relationship or a negative relationship. And so in order to be able to use gamma and have it look in a way that's meaningful for those patterns, there has to be sort of a meaningful ordering in those variables. And so it can't just be sort of region of the country where I could swap them around in any particular way. Instead, there should be something like, strongly disagree, disagree, neutral, agree, strongly agree, where there's a built-in progression that makes sense. And we can maybe flip it around. And so start with agree and, and end with, start with strongly agree and end with strongly disagree, or vice versa. That's fine, but the ordering internally it sort of makes sense and wouldn't make sense to muck around with. Whereas chi-square can be used with nominal variables. You can use it with ordinal variables, that's certainly possible, but it also can be used with nominal variables because it's not asking, is there a particular pattern, linear or positive or negative? Instead, it's asking, are certain combinations of cells more likely to occur and some combinations of cells less likely to occur? And is that more or less than we would expect to see? So it's sort of asking a different kind of question and therefore can be used on a different kind of variable. If we're thinking about sort of when we would use these measures, gamma is pretty versatile. There are some statistical measures that work better for tables that have sort of, that are symmetric, where it's like I have 2 rows and 2 columns, and some measures that work better when you have like 3 columns and 2 rows, and or they could be arranged different ways. Gamma will work pretty much on any table and gives you more or less comparable results to all those other measures, which is one of the reasons why I think it's probably the one to be familiar with. And it works pretty much under any conditions, assuming you have ordinal variables. Chi-square is a little finickier. It tends to not be quite as good when you have low expected cell counts. So if you have a couple cells in your table that just have very few cases in them, that may not give you the best reliable, consistent chi-square values. Likewise, if you have a large sample, larger than 1,000, chi-square is going to ping that there's a pattern pretty easily. It stops being as useful of a test because it starts picking up everything as a statistically significant pattern. So it tends to work better when we have a couple hundred cases where there's enough to sort of fill out the cells and you kind of see the distribution within the cells, but not so many that kind of overwhelms the sensitivity of the test. The last thing I'll maybe flag is that linear piece. And I've talked about this a little bit, but I really want to stress it, that gamma only looks at, is there a positive relationship or a negative relationship? And it communicates that positive relationship or negative relationship in a number that runs from -1, which is a perfect negative relationship, to 0, which is there is no relationship here, to to +1, which is a perfect positive relationship. And so in between there, you can have any value. If it's 0.8, we would say that's a strong positive relationship. If it's -0.5 or -0.4, we'd say, oh, that's a moderately strong positive relationship or a negative relationship. If it's 0.2, we'd say, oh, maybe that's a weak positive relationship. So we can sort of interpret that range as telling us something about how closely the cases are sort of following a linear pattern within that table. Interpreting chi-square is maybe not quite as intuitive. There's no sort of set scale of -1 is a perfect relationship or negative relationship, +1 is a perfect positive relationship. With chi-square, what it's asking is, we've done an analysis on this table to figure out sort of what we would expect to happen if cases were distributed according to their row totals and their column totals and sort of how the table breaks down. And then we look at how the cases actually landed in the table. And are there more cases in some cells than we would expect and less cases in other cells than we would expect? And we'll sort of take those differences and add them up. And if we get a large number, that means that there's something going on where cases are landing differently than we would expect. And if we're getting a small number, cases are actually behaving more or less as we would expect. And so there's probably not a pattern. And so with a chi-square value, the larger the number is, the more that indicates that there's a pattern going on in your data, and the bigger the pattern is. Now, how big is a big chi-square value? It's where it gets tricky. I don't actually know, because it depends. It depends on how many cells you have in your table. And it depends on how many cases you have in your table. And so that line separating like not particularly interesting chi-square value from, wow, there's a pattern here that we should pay attention to, it moves depending on those other things. And so it's oftentimes easier to convert a chi-square value into a statistical test that will tell you, is this likely sampling variation, or is this something important and noticeable? And we'll talk about hypotheses testing for at a later point. But for now, just know that the larger chi-square value means that there's greater evidence of a pattern going on in that table. Okay, and then a final sort of measure of association between two variables that we'll talk about is Pearson's R. And that would be used when we have continuous variables. And so we can take continuous variables and we can plot them on scatter plots. That ends up being a really powerful tool to be able to sort of visualize what's happening in our data. And it ends up being a better strategy than taking continuous data and trying to smash it into a table. And so we can look at this pattern and say, oh, wow, that seems like kind of a positive relationship. So as I move in a positive direction to the right, the cases seem to be going up in a positive direction on the y-axis. And I can sort of look at that and say, oh, I can see that. There's maybe one or two cases that are behaving a little bit weird, kind of over on the extreme end, but by and large, they kind of track in this sort of line pattern. And so in addition to just sort of being able to eyeball that with a scatter plot, I can use statistical measures that sort of quantify how closely those dots are following that sort of straight line pattern, or how spread out and messy they are. And so when we're thinking about that, the measure that we use is Pearson's R. Sometimes it's called the correlation coefficient. If we're talking about correlation, we're talking about Pearson's R almost always. When we're talking about gamma, we oftentimes call it correlation. I think it's technically association, but Pearson's R ends up being really important in statistics. It is the foundational statistical building block for what we call regression, which is a statistical technique we'll talk about in greater detail later, that allows for us to do some really interesting things. But it's also worth understanding sort of the limits of Pearson's R. So Pearson's R is a statistic that produces values similar to what we saw with gamma. -1 is a perfect negative relationship. So it would be points starting at the top and trending down in a straight line. 1 is a perfect positive relationship. So points starting at the bottom and trending up in a perfectly straight line. And 0 is just patterns that are sort of randomly spread out all over the place. Well, actually, maybe. That's sort of the assumption. The assumption is that there is no relationship whatsoever. However, it's important to point out that the assumption is that as you go from like 0 to 1, your points are sort of compressing in closer and closer and closer around that straight line, but not every pattern is a straight line. Sometimes we see patterns that are maybe curves, maybe they're sort of a parabola. Pearson's R is going to have a really hard time figuring out what that is, because it seems like it's going up in a positive direction, then it seems like it's going down in a negative direction, and that could actually end up canceling out and resulting in a zero correlation, suggesting that there's no pattern, when in fact there is a pattern. Similarly, if you have sort of a exponential relationship where sort of things start out slowly and then sort of gain acceleration as they go, Pearson's R is going to underestimate that pattern because it's going to try to treat it like it's a straight line and not really recognize what's going on. And then lastly, I'll flag that while we can use Pearson's R, the correlation coefficient, on ordinal variables because they are lined up and they oftentimes have numbers associated with them, this is really bad practice because with categorical variables, the numbers that we assign are arbitrary. I can code strongly disagree at -100 and strongly agree at 2, and strongly disagree at -99 and agree, or and I should say disagree at -99, agree at 1, and neutral at 0. And that works ordinally because I can sort them and they'll line up in the correct order. But if I'm using Pearson's R, it's treating those numbers like they're actual numbers. It's trying to do math on them, treating them like they have actual values where the difference between one category and the other category is a mathematically meaningful unit rather than something I arbitrarily created to assist in my sorting process. So people will frequently use Pearson's R on ordinal variables, and it will give you results that potentially are interpretable, but it's bad practice because we're making assumptions about those differences between categories and the numbers that represent those as having mathematical meaning rather than sorting meaning, which is not the case.